Good morning, students. This is Mr. Marquetta, and I'm here to work with you today on Chapter 5. The reason why we are making this video is because when we were supposed to meet on Wednesday this week, the classroom that we were scheduled to meet in was not prepared properly for our lesson, and I had to cancel our classes. It was a little bit inconvenient because I did come very far to come and work with you, but when I got there, I tried to fix the issue, and then tech tried to help me by directing me over the phone to do certain things with the computer that didn't work. And then they sent somebody, a really helpful person named Dave, and he worked very hard on trying to make it work in our club room. And ultimately, we found ourselves at a standstill and we couldn't fix the issue. So as a consequence, I offered to help everybody study today instead, where we have sorry about that, where we have our lesson on Saturday instead. And it's being recorded right now. So we're going to have this posted shortly on eCampus. And this is an optional meeting. You don't have to come to this class if you can't. It's Saturday morning. Our class is supposed to meet on Wednesday. And instead, we're meeting today, and I'm going to go through Chapter 5 with you. Also, the homework associated with Chapter 5 has been pushed forward to be due on October 4th, hoping that that will give you more than enough time in this odd situation to be able to manage Chapter 5 and carry on with the homework. All right, so that being said, I'd like to begin our lesson now. We're going to talk about two-way tables. And while you're here in our Zoom, please feel free to unmute yourself and say something if you have a question, or feel free to type something into the chat. If you have a question, I will address it there. And today we're talking about two-way tables. We're going to focus on 4 important objectives today. We're going to talk about two-way tables and what they are and how to use them and what the point of them is. We're also going to talk about marginal distributions and conditional distributions. And then we're going to touch on Simpson's paradox and talk a little bit about what that is. I'd like to start by talking about some of these important words. For me, when I reviewed this PowerPoint, thinking about how I was trying to prepare to help you all learn how to do these things, one thing that kind of stood out in my mind was they very loosely use the word distribution. And I'm not sure that we all really understand what a distribution really quite is. I just want to make sure that that's clear before we start talking about kinds of distributions like marginal and conditional. So a distribution is a bunch of numbers. And I want you to, every time you hear distribution, just think of it as a bunch of numbers or a bunch of data. It's called a distribution because if you could imagine what it means to distribute means, for example, a teacher would distribute worksheets to a class. To distribute means to share and pass out and make sure just about everybody gets one and that there's enough around for everybody. That's what a distribution or to distribute means. A distributor in a company does just that with trucking, So a distribution is nothing more than a bunch of numbers. These are the numbers that came out in my measurement for my tests or whatever. Next, we have the idea of marginal versus conditional. And the reason why we call them marginal distributions is because they have to do with two-way tables, meaning that it's something of two categories that you would fit in. And then we have conditional distributions, which is if we were only talking about one of those categories. So the marginal distribution and the conditional distribution, they're based on the idea of a bunch of numbers and then certain kinds of measurements that you could do to a bunch of numbers. All right, that's what we mean by those ideas of distributions. Now, let's talk about a two-way table. What is a two-way table? It's going to summarize two categorical variables. So it might be I ask you two things like, what is your favorite ice cream flavor? And then I ask you, how many times have you gone to the ice cream parlor? Or something like that, but it's two different questions. And it should be something categorical, like in other words, how many times did you go to the ice cream parlor? You can only answer 0 or 1 or 2 or something like that. What are your favorite ice cream flavors? Strawberry, chocolate, or vanilla? And when it comes to two-way tables, it is about categorical data. So I want you to try to remember that idea. I'm not asking about numbers, I'm really asking about words. Maybe a better example would be, what's your favorite ice cream flavor? And then what's your favorite chocolate bar? And we could put some people in certain categories and put others in others. And ultimately, you'll always land in two categories. You'll land in the category of what your favorite ice cream flavor is, and then you'll land in the category of what your favorite chocolate bar is. And there'll be a number of people in the study that will land in that category with you, and there'll be a number of people that fit both of those criteria. And then for all the other kinds of criteria out there, which there should be, basically how many ice cream flavors times how many chocolate bars, that's how many different categories you might fit into, because you're going to have a preference for one of each. So each factor has a number of levels. So for example, the ice cream levels are strawberry, chocolate, and vanilla. The chocolate bar levels, maybe they're Heath and Hershey's and Payday or something, but those are the levels, And you might imagine what it might look like if I put one category here and one category on the top. That's what a two-way table is. We like to call it an R by C table, meaning this one is a 3 by 3 table because I mentioned 3 ice creams and 3 chocolate bars. But we always identify the dimensions of our two-way table by first saying the number of rows, meaning the number of categories that are going across, and then the number of columns going down. So it's row by column, just like a matrix, if you remember studying matrix algebra back in high school. All right, so here's a great case. Now I gave you a very easy one. Oh, it's keep calling it strawberry. It's ice cream and chocolate bars, right? But here we are in mature statistics. So here's a very practical question. Let's talk about there are some people that have parents who smoke, and then parents who don't smoke. And then there's some people that have one parent who smokes. That's 3 categories. So if I asked you, what is the smoking status of your parents? You might either say, neither of them smoke, one of them smokes, both of them smoke. And then I can ask you specifically, do you smoke or not? Now there's 2 levels of that. Either you smoke or you don't, see? So in this situation, you're talking about one factor that has 3 levels, your parents' smoking status, and then the other factor having only 2 levels, your smoking status. Looking something like this, let's pretend for a minute that this is our two-way table. It would be a little bit more practical if I had on the left here, and they didn't really put this together very well in the PowerPoint, but there should be somewhere right over here, and let me illustrate for us. Like right around here, you should have also right here, something like both, one, none, something like that. In other words, so that you have categories listed on the left and then across the top. I don't know why they put this in this way. They should have put it that way from the beginning. On the next slide, you'll see it's been repaired to be that way. Let's just move to that slide and you'll see what I'm talking about. Okay, so here, I'm going to try to illustrate with some little rectangles. All right, over here we have the first category, your parents' smoking status. And over here, we have the second category, your smoking status, okay? And then we have people we have 6 different groups now, because we have people whose both parents smoke, but they smoke, there's 400 of them. Both parents smoke, but you don't smoke, there's 1,380 of them. And then there are people that have one parent who smokes, but they are also smokers, that's 416, and so on. So this is what we call a two-way table. It has to do with 2 questions. It's very much like bivariate data, but it's for categorical data and not numeric data, okay, or quantitative data. Now, what do we mean by a marginal distribution? A marginal distribution has to do with when I take a table like this and solve it. In other words, how could I solve this? Well, I could add across, and I'm going to use highlighting for that. I can add across. Hold on, friends, I'm almost there. There we go. So I could highlight across, like I could do these 2 numbers, and I'm going to get this one if I add it, right? Then I could do the same thing here. Add these across and put it here. Get the idea? And then carry on that way. And then likewise, I have to add downwards as well. I'll use blue for that. So let's say that I added downwards. I would add and I would get this. And then I could do it again to the other column. Add this way, I should get this one. Right? But either way, whatever I do, this across and this down are going to always add up to this. And this is the ultimate sum of the two-way table. Now, we're calling them margins, okay? The little sums that you have found in the green rectangle on the right is a marginal distribution, meaning it is the distribution or group of numbers okay? That represents all of the sums of all of those different categories. Same thing on the bottom is a second marginal distribution in that nice blue rectangle. Now you can take those actual little solution sets, 1780, 2239, and 1356, and then the other set, 1004 and 437, you could take those and make little bar graphs out of those, and that's called the marginal distribution, okay? So let's review. We give you a situation about, this time it's about parents smoking and students smoking. And then you take those numbers and you solve the table by adding across and adding down, and then ultimately adding all to get that number. That's the final sum. And then what you could do is focus on just the sums across, which is the green box, and make a bar graph of that. And then we'll focus on just the sums that are on the bottom in the blue rectangle and just make a bar graph of that. And those are your marginal distributions. So what is the actual marginal distribution? In the rectangles, you can see them there. All right. Something like this. And then if you wanted to, you can convert those marginal distributions into percents. Now, just as I mentioned in the last one, this certainly is a marginal distribution, but it's about raw data here. It's not about a percentage. You can use those, or you can change them all into percents like so. How do we do that? Well, remember what the whole is. The whole is this number right here, right? So since that's the whole, I can take this number, and let me kind of illustrate it with a little arrow. I could take this number and divide it by that number, and it will give me this percent. Likewise, if I wanted to figure out, let's do, what is the percent associated with this figure here, right? I would take that number and I would divide it by the total, which is here. I'll circle it again, right? And then after I divide it, change it to a percent, and then this is the marginal percent associated with that figure. So what will happen is, instead of in the green box and blue box having raw data numbers like 1780 and so on, you'll have all percents in there instead. And just like we talked about earlier, you could take those percents and put them in little bar graphs and make marginal percent distributions out of them. The thing about it is, whether you do it with raw data or percentages, it should still be the same geometric figure, the bar graph. And that's kind of crucial, and that's part of our lesson today. Okay, so this is what we mean by a two-way table, and this is what we mean by marginal distributions and marginal percents. I want to throw in for a minute, we have not talked about conditional percents or conditional probabilities yet. And I want to reiterate with you, this is using all of the numbers to get your answers. And we're using all of the numbers primarily right here. That number, 5375, is the sum, the grand sum total of all 6 numbers in the original two-way table. That number is being used as our denominator. And when you're finding a marginal probability, or marginal distribution rather, you're using all the numbers in the table because your denominator encompasses all the numbers. Now, when you're doing a conditional probability or a conditional distribution, you're not using all the numbers. So I want you to remember that this is the one that's a little bit easier. I would argue marginal is easier than conditional, because marginal, you're just using all the numbers there. But conditional, you have to watch carefully and make sure you pick the right numbers to use. Okay, so let's talk about what it would look like as a graph first for marginal. Before we go into conditional, let's look at marginal graphs. This is an example of what you're going to be asked to come up with using marginal distributions. And you can see here, we've used the percent marginal distribution, and we've chosen to use across the bottom our categories, both parents smoke, one, and neither. And then along the side here, I have the percents of students that were interviewed. And this is only the people that have, this is only the way that it goes from parents smoking. So that's the 3. Now, forget about that. That's the green one. Remember the green box? Let's go back for just a second. Remember the green box? The green box is about all of the different parents. In fact, in one of the slides, it tells you, see in the green box is illustrated as marginal distribution for parents smoking. There's 3 numbers of that. There's 2 numbers of the distribution for students smoking. And look, it's blue. So look at the graph for the blue one. So it's like I said, you take the actual final answers on the column and the final answers on the bottom row and make bar graphs out of them, and make sure you title them according to what the category is. Like in the blue graph, that's describing the cases of students that are smokers and students that are not smokers. Look at the title, student smoking. And it's the same thing with the green one. So it's important to make sure you title them correctly, because whenever you come up with bar graphs for a two-way table, you will be getting two bar graphs and you have to know which one is which. Okay? All right. Now let's talk about conditional. Conditional distribution works in this way. If you have the two-way table and you're not interested in all of the people in the study, but only those people that have one specific criteria. Like, for example, this is a lot of great data, but I'm only interested in students who have both parents who smoke. Okay, now if that be the case, then I'm going to ignore all of the other numbers and only look at the bold numbers. Look at the numbers that have been made bold in our table. For the conditional distribution, if we say a specific kind of question like, what is the percent of students who smoke when both parents smoke? And I really want to harp on this word right here. I'm going to highlight it in pink, all right? When, see that? That when means that you're talking about a conditional distribution. What does it mean when? All right, well, you can go out when it's nice outside. I don't want you to go outside when it's a wild hurricane outside. You can go outside when it's nice. Now you have a condition on it. That's what a condition is. Only when this is the way it is, then can you say this is going to be happening. So only when my students have both parents smoking do I want to look at their numbers. If they have one parent smoke, I don't care. If they have neither parent smoking, I don't care about those numbers. This is what a conditional distribution is that there's a condition on it. The condition this time is your parents have to both smoke for me to use your data in my study right now. Okay, so a conditional distribution involves only the bold numbers you're seeing here. You might have another kind of condition, and I'll use a different color. Say it was like, and I'll use black for this one. Say it was, my condition is now I only want to look at students who do not smoke. Then I would be looking at these numbers only, and I would ignore all the others. So can we remember, friends, that the marginal distribution is just add everything up and use the big denominator, which is 5375, right? But when it comes to conditional distributions, your denominator is not going to be 5375. It'll be the sum of whatever the category is. Specifically in this case, you're going to be using this as your denominator, or in this other case, you'd be using this as your denominator. So the real thing that you have to remember is the conditional. You're not using the grand total, you're using the total of the condition. Okay, now let's look at one example here where we're talking about the percent of students who smoke when both parents smoke. See how it says when both parents smoke? That's how I know that I'm going to be using this right here. I'll use a circle to show this one. I'm going to be looking only at this column right here, this row right here. Okay, and now that I'm looking at that, if I want to know when both parents smoke, that tells me that my denominator will be 1780, like you see right there. And we also want to know the percentage of students who smoke when. Okay, so how many of them smoke? 400, right? Now look at my numerator. Okay, so I hope that that's clear. That's how you find a conditional distribution, is by the specific thing you're looking for over the sum of everyone that has that. All right, once more, marginal distribution, the denominator will be right here. And for a conditional distribution, your denominator will be one of these. Okay? Next, comparing conditional distributions helps us to describe the relationship between two categorical variables. And when we compare the percent of individuals in one level of factor 1 for each level of factor 2, substantial differences suggest an association between factor 1 and factor 2. So what they're trying to say is, if you look at this and you find all those percents, you might be able to find patterns and different connections, and then you can start trying to make suggestions or assumptions to see if you're on the right track with your thinking, and to use data to try to support your ideas. But the way that you start is by going and finding all of the percentages and finding all different kinds of conditional distributions, just to see if there are any matches or what it might be. Okay, so it's the kind of thing that after you understand the concrete logic of solving your two-way table and how to get all of the different distributions you need out of it, then the critical thinking comes into play, where you have to start saying, how can I use these numbers? What can I use them to support? What ideas can I support with them? And what am I trying to say about students who smoke with the same ideas about their parents smoking or not as part of the story of students smoking? And that's what you've got going here. Okay, let's take a look at what a conditional distribution would look like here. So here are some examples of conditional distributions. And for these examples, friends, I'm going to kind of flip back and forth a couple times. I'm going to be going back and forth between our PowerPoints. So the last slide has all of the numbers, and this slide has the actual percentages. I just want to verify with you how these all come about as some basic exercises so you could be comfortable with conditional distributions, okay? Let's start by taking a look at this one. And we have the percent of students who smoke when both parents smoke, okay? So the when is when both parents smoke. And I want to know about percent of students who smoke. So who smoke? The student smokes when both. All right. Students smoke when both. So if it's when both, then what I need to do is I need to use both parents smoke when both means I'm using this number here. This is the total of all the students who have both parents smoking. Of that group of students, there are 400 who do smoke. My arithmetic should be 400 divided by 1780 for that question, because the question is saying, what is the percentage of students who smoke when both parents smoke? Here's when both parents smoke, and here's the students in that group that do also smoke. Now take a look at the way it's written. 400 over 1780, right? And then we divide and get a percent. So that is the conditional right there. How about the second one, the percent of students who smoke when one parent smokes? All right. Well, when one parent smokes means that I'm talking about all of these people here. Right. And I can't remember what the last one was. Hold on a minute. What was it? It was percent of students who smoke when one parent smokes. Okay, so when one parent smokes is 2239. The percent of students who do smoke is that number 416 there. So it ought to be 416 over 2239 to get our answer this time. And then after you're done with that, you could go ahead and change that into a percent. So there's your 416 over 2239 right there. And our solution there is 18.6. One more case and then we'll move on. How about the percent of students who smoke when neither parent smokes? Okay, so it's students who smoke when neither parent smokes. So when neither parents smoke, it's looking to me like that number would be this one. And then the number of students who smoke is 188. So the arithmetic should be 188 divided by 1356 and change it to a percent. 188 divided by 356, I got it right here. And it gives you this as your solution. Okay, so it should be not that hard to do conditional distributions, especially seeing these great cases. Just please remember, friends, for marginal, you divide by the grand sum. Okay, for conditional, you divide by the when, or whatever the condition is. In this case, when neither parent smokes. All right, so that's our conversation about two-way tables. Let's talk about the graphs. You could come up with something like this for conditional. In our textbook, they like to use bar graphs, and they like to use a stacked bar graph, and I'll talk to you about how those work today too. The conditional distributions can be compared graphically by displaying the percents making up one factor for each level. And conditional distribution of student smoking status for different levels of parenting status would use these specific values, the 22, the 19, and the 14. Let me highlight those. All right, and that's what you're looking at here. What we did was we chose both parents smoke, one parent smokes, and neither parent smokes as our three labels on the x-axis. And then we included nice rectangular bars for each category. Okay, both parents smoke was 22%, that's this one. And then one parent smokes is 19%, that's this one. And then of course, neither parent smokes is right here. Now, I'm going to show you today also, before we dismiss, how to use Excel to come up with these beautiful graphs and how to change them and make them just right. And it can be a little bit tricky, which is why I deliberately made a guide for you, like we do for every chapter, about how to come up with graphs in Excel, or how to use Excel to succeed in this chapter. So we're going to go over that today too. I have that on hand. And after the PowerPoint, I'll come back and I'd like to show you a little tech of how to come up with these graphs. Okay. If Very good. Now, conditional distributions of student smoking can also be given in a pie chart. So if you want, you can either make a bar graph like we did before, where you have 3 bars representing the 3 categories, or if you wanted to, you could have had a pie chart with 3 parts. What we did to illustrate what it's like to do a pie chart was we did conditional again, but instead we did conditions for each of the 3 categories here. And we have, instead of adding downward, we're adding across. I want to just reiterate that. Take a look at the last slide one more time. I want you to notice, looking at this with me, that right here, we have hundreds on the right. See that? That's kind of crucial. And here we also have hundreds on the right. The fact that we have hundreds on the right, oops, I'm sorry, friends. The fact that we have hundreds on the right, let me go and highlight that, tells you that there are going to be 3 circle charts or 3 bars. If you were instead going with the other condition, which is when parents smoke, or when you smoke, or when you don't smoke, and there's only 2, then what would happen is you'd be looking at 100% on the bottom in this position here. And we're going to look at that too. And in that regard, you'd have only 2 bars or 2 circle charts. Okay. So here we have the same data, exactly the same data, but given as 3 separate pie charts. And it's 22 versus 78, meaning that we're showing the entire 100% here in the 2 parts that we could. Notice there also is a lovely little legend here with color to show you which part is representing which piece of the distribution. And again, when we do in Excel, there's a really simple way to come up with a pie chart that looks almost exactly like this. And that's also in our guide today. And I'd like to show you how to use a 2-way table to come up today also with circle charts as well. Or I think they call it pie charts in Excel. Okay. So again, you could just go and figure out when you get your percentages where they go. Also, let's talk about how do I get those percentages? How do I get those percentages? Well, if you go back and look at the original graph table, you'll see that it's been converted. Let's go back one more. These numbers right here, I can convert them all considering that this is the 100%. In other words, I could think about 400 divided by this number and put that percent right there. 1380 divided by that number and then put it there, and carry on. Take 416 and divide it by this number and put the percent there. And if you do all that carefully, then you'll be able to get a percent distribution like you see here. And that's the first time they show it. Also, please note, since it's a part of the right-handmost column, all the right-handmost column figures become 100%. And also, please note that here, these are going to always add up to 100%. And so are these. And so are these, because as you move across, they're 100%. Now let's use that information and think about what it's like to make those into circle charts instead. If I make them into circle charts, then I have 3, 1 for each category. I have a both parent smoke circle, I have a 1 parent smoke circle, and then I have a neither parent smoke circle. Sorry. Okay, so hope that's clear. All right, now let's imagine for a minute, instead of having percentages across, where the denominator is always going to be this thing on the right, now what I'm going to do is I'm going to make it that the denominator is the thing on the left. So here we have the same data, but changed. Let me tell you how they got those percents. I'm going to go back once more. In the raw data, I would say, okay, so for this particular spot, I'm going to write in that spot the answer to what happens when I take 400 and I divide by 1004. That percent is what I'll put there. Likewise, I'll do the same thing again for what happens when I do this figure divided by this figure again, the sum, right? And I expect to put that answer right here. Let's do an alternative one over there on the right. For example, if I was trying to figure out what the percent is that goes right here, I would take that number and divide it by this, and then put the answer right here. Notice that in the same way before, the bottom total just totally dropped out. Here, when we're doing the condition being your smoking status, the right-hand column just totally gets removed altogether. All right? So, that being said, let's move forward. And as you can see right here, these figures are going to all add up to 100%. And so are these. because they've been found using those divisions like I explained. And now, instead of having 2 parts to every circle, you'll have 3 parts to every circle, but notice you'll have 2 circles. See how the 2 times 3 equals 6 keeps showing up in different ways. Like in the last one, you see the number, the idea, in the fact that you have 2 circles, each with 3 parts. That's 6 little parts. Same thing is happening here. I have 3 circles with 2 little parts. Again, there are 6 total parts. So the row by column thing, the fact that we have 3 by 2 in our 2A gives you a hint that there should be 6 parts total when you make your graphs, and you can use that as part of your analysis. Make sure that you have your complete data all there. All right, so one more time. Here, this would be the situation if we made the condition when you smoke, meaning how many students have 2 parents that smoke when they are smokers, or when they are not smokers. And that's what the percentages you're looking at. It's basically the idea of trying to change the wording around. So instead of it being, what is the percentage of students who smoke when they have 2 parents who smoke? And then instead saying, what is the percentage of students who have 2 parents that smoke when they are not smokers? So the when tells you what the total is. And that's conditional distributions, guys, okay? I hope that was clear. That's kind of about all there is to it. There is a little bit of a weird stacked graph we're going to talk about also. We'll talk about something called Gallup. Gallup is an interesting thing that comes up often in statistics. It sounds like when you're on a horse and you're riding fast. Gallup is one of the most advanced and most appropriate scientific polls that we have. And you can use Gallup poll data to get really strong answers, because Gallup polls are very authentic and very unbiased and carefully created. So Gallup is kind of our go-to in statistics a lot when it comes to concrete findings and data. Now, here we have an example of a Gallup survey that had to do with a certain specific situation, and we have a 2-way table. I'd like to talk to you about this one and illustrate a little bit with this. Also, this is a great example of what it looks like to use a stacked bar. In 2013, Gallup survey investigated how phrasing may affect the opinions of American adults regarding physician-assisted suicide, and here are the findings. Which choice describes the value of 70%? So let's take a look at this table and try to understand how this is going. We have 2 different forms, meaning we could describe the idea in 2 different ways. We could either say, well, we're talking about patients who will end the patient's life by some painless means. Or we could also say it this way. We're going to talk about physicians who assist the patient in committing suicide. Now listen to the 2 wordings. They are significantly different. They might provoke certain kinds of emotions when you're looking at them. And as a result, you may think, yeah, that should be allowed. Or you might say, no, that's not right. That shouldn't be allowed. In other words, there's 2 conditions. Either we have some people who say, we're going to end the patient's life by painless means. And then of that group, we have people that say, yes, that should be allowed. Then there are people that say, no, that shouldn't be allowed. And then there are people that say, I don't care. I have no opinion either way. Then there's another way to say it. And we say to the group, okay, how many of you think assist the patient to commit suicide should be allowed? Should not be allowed? No opinion. So again, this is a 2-way table. It's not that different than what we talked about before, where we had smoking versus your student smoking versus parent smoking status, because it is ultimately, again, a 3-by-2 table, just like before, which keeps us in gear with what we're doing and in the same mindset. But I want to warn you, often they're bigger than this. They're not 3-by-2. They may be more or they may be less. But we're kind of sticking to that general framework to kind of keep the ideas flowing. And in this situation, as you can see, we already have some conditional probabilities. So notice that we do have figures that add up to 100 each time. For example, 70 and 27 and 3 will add up to 151, 45 and 4 will add up to 100. And also we have the total amount of people interviewed right here and here. So if I wanted to, for example, I could find specifically the exact number of people in Form B who have no opinion by doing 4% of 816 and so on and so forth. Which of these best describes the value 70%? I want you to read carefully each of these 2 things. Is it a marginal value representing the proportion of respondents in favor of physician-assisted suicide? Or is it a conditional value representing the proportion of respondents in favor of physician-assisted suicide, given that the question was in Form A? The answer is going to be B this time. The words given that is the same as when we talked about when, how it illustrates what a specific condition would be. And here the question was asked in form A. If we're say given that the question was asked in form A, then that's telling you when it's form A means your denominator is this number here. So it's certainly a conditional. Where would we see the answer for part A? Let's talk about that for a minute. Where is the marginal value representing the proportion of respondents in favor? That would be the number that would have been right here, right? Because this is the people that believe it should be allowed, regardless of how it's phrased. It would be the sum of whatever this number is right here. We don't have enough information to answer that, actually. Well, we could. We'd have to find 51% of 816, and then 70% of 719, and then get that number and put it here. But I don't know if you'll be asked to do all that work, but if you needed to find it, you could. And I just want to mention for part A, that's what we would expect for you to do. Marginal is when you have numbers on the outside like this, or numbers on the bottom like this, all of them. Conditional is when you have a percentage that has to do with one thing here and one thing here. Now, here we have percentages again. The data may be analyzed as percentages or totals. And in the bar chart on the next slide, you'll see the percentages being stacked. So here, what's happened is they've changed it from percents into actual numbers. And that's not hard to do. Like I said, all you have to do is just realize that the actual figure that goes here is really 70% of 719 and write that in. Likewise, this one would be the actual answer to 45% of 816 and write that in, okay? So if you had that, you could create a nice stacked bar graph like you see here. Likewise, if you wanted to, you could do this for percents, but this is better for raw data because we could see that the wording commit suicide is actually a taller bar than the painless means bar. And that's also crucial because you also see that there are significantly more people who went with the one than the other in different ways. And we are dividing in terms of specific categories, like from 503, then above that we have 194 more, and then above that we have 22 more. So here's the 503 mark, here's the 194 mark, and here's 194 above that, and here's just 22 above that. And we also have a really nice little legend here that we could use also. All right. Now, when you do these in Excel, and I didn't include this in the Excel guide that I made, but when you do them, it's just a matter of clicking the other one that has it stacked because there's like an option of what to click. This is really very easy to make in Excel. And if you're okay with making the other graphs in Excel, this will also be just the same as that. It's just a matter of clicking the right one and it pops right up. Okay. All right. The next thing I'm going to do before we jump into Simpson's paradox, I'd like to work with you a little bit now in Excel and talk to you about how to do these different ideas in Excel. If you go to eCampus, you'll see in Module 5 that I did create an Excel activity, and I also included the Excel answer guide too. And right now what I'd like to do is work through the Excel activity with you. So let's share that. Okay, sorry, a little confusing, but this is the way I wanted you to see it today. What I have in front of you now is on the right, I have the Chapter 5 Excel operations that I posted on eCampus Press. And on the left, you see I have the Excel spreadsheet that I created so that we could play around with it, okay? So let's work through this Excel activity. And as we're going through it again, I invite you to contribute or ask questions by unmuting or by throwing things into the chat, okay? First, let's talk about how it would be to find the sum of any row. The way you would do something like that is you would highlight the row you want to find the sum of, and then you would hit, and I'm going to open this up. I'm going to keep opening this up and closing it. I would add this up this way. I would first highlight them, and then I would hit the sum button, which is right here. And there's the answer right there, quick and easy. Let's do it again. All right, now let's do it down. Oh, but there's one more row. Let's do this one too. Okay, now let's do it down. All right, and then to get this one, all I have to do is add these. Oh, wait a minute, you can't do that. And I did include that. Instead, to get this one, you hit equals, sum, and then you highlight any numbers you want to add up. For example, I'd like to add up all of these. There you go. You could also have done that by hitting equals sum and then getting these three here, like so. Yeah, that won't let you do it, but you know why? Because these are already come about because of a formula, so you can't use them again. So can we remember when it's time to do the grand total? You write equals sum, and then you get that command, and then you highlight what you want and hit enter. All right, so now I've solved two-way table, and I found all the marginal distributions. Let's put this over here now. All right, so carrying on, to get a marginal distribution, we would copy it and we would get rid of all the sums. The way I do that is by highlighting everything I have. Here I go. And now at this point, I can either right click and say copy, or I could just say Control C, and you'll notice that it's dotted lines animated. That means, okay, I'm ready to copy this. Where do you want it? That's what Excel is saying. I'd like you to copy it starting at this very cell right here. So go to the cell you want to start. Maybe I'll bring it down here so I know it's a different one. Control V. Here it is again. So I just totally copied a piece of cake. Next, I'm going to delete all of the sums except for this one. I'm going to leave this one in here. And to make things easy, I'm going to write the actual number 1018 there. The reason I did that is so that when I click the cell, it doesn't have a formula up here. It has the actual hard number up there. So now that I've got that, I could start thinking about finding the marginal percent for each one. What I want to do is figure out this number 300 right here. What part of 1018 is it? So I could do that by coming over here and saying equals, and then I'll take the number 300 and I will, oh, well, I could either do it that way or I could do the sum. Let's do it the way that the activity says, equals the sum. And then select that one. And it's the sum of all these, and then close the parentheses. So in other words, I'm telling Excel, okay, the numerator is the parentheses of the sum, and then divide by, of course, the number that is the total. This time, the number that is the total is 1018. All right, let's do that again. Equals the sum of all these numbers, close parentheses, but then divided by this. Once more. Oops, careful. And then divided by this. Let's do it here now. I'm going to take, for this one, I'm going to find the sum of all these equals SUM of all these figures, close it, and then divide it by the total. The total is right here. One more time. For this one, equals sum of all three of these. That didn't come out right. Do it one more time. Equals sum of all three of these, close, divided by the grand total. Okay. You're almost done. We'd like to make them all percents. So now I'd like to show you how you're supposed to change them into percents. I take the numbers I want to change into percents. And then I right click. Well, let's do them one at a time that way, because that was a little bit confusing. Let's do these three first, and then I'll do it again to just reiterate. I want to change these numbers to percents, so I right click it. And then I'm going to go to, I have it here. To change it to a percent, it's right here. Format cells. And then when you say format cells, I don't know if you could actually, yeah, I hope you can see it. You should be able to see it. Over here, let's change it to a percentage. And you can make it look like, see, it's a sample. If you want, you can make it look like that. Or if you want, you could tell Excel to always round it to a whole number percent by making this 0. See how I can have as many as I want? See the point? I want it to be a simple percent with no decimals. So I could change it to a 0 and say, okay. And look, my numbers have changed to perfect, simple little percents. Let's do that one more time. Please change these into percents. What do? Highlight them, right click, then go to Format Cells, then select percentage, then identify how many points you want after the decimal point, and say okay. And now they're all percents. Isn't that great? That's how you do it. All right. Now, let's make some marginal distributions. How can I do that? Well, what you want to do is, let me get this into view here. What you want to do is highlight the percent you're trying to make a distribution for and then click insert. So that would mean, I'm going to open it up now. I'd like to make a marginal distribution for these first. So I highlight it, I say insert, then I come over here and I click this little icon right here. Wait, this icon? You know what? Let me look at it one more time. Yeah, it is this icon. And now select the first one you got. And look, there it is. There's your answer right there. There's a marginal distribution. You got to doctor it up a little bit, fix it a little bit. Let's talk about how you would fix something like that. It's over here. How would I fix something like this? Well, first let's change the title. I would double click the title and just put in there, get out of there. And just put in there something. Let's move this over so I can get that ping if I need it. I don't even know what the data is anymore. Forgot. Whatever the data is. Oh, college for children versus parents, or whatever. Make up some kind of title. You know, capitalize. Okay, let's be grammatically correct. You know better. All right. Next, if you want, you can include percents by clicking at the plus to the top right of the bar graph and then selecting data labels. So I would click on the graph and click the plus and go to data labels. And look, the percents got it. Look, the percents have appeared. Doesn't that help? That's great. Next, let's change the labels. The way you would do that is by clicking axis titles. And now there are labels there and you can go and change them. Category 1 or whatever you want to call it. And likewise here, right? Category 2 or whatever. And as for the example, so you could see, so you could name them whatever you want. And now this one is kind of important and I want you to pay close attention to this. You could change the names for the categories. Like right now it only says 1, 2, and 3. Okay. And I want you to pay close attention to this one because this took me a while to figure out. And it's really not very hard at all. It's just a matter of kind of knowing what you're doing and doing it just right. First, click on the category so a box appears around them. Now look, if I click on the category, the box appears. I want to tell you, if you click on it and you don't click the category, the whole thing appears. See that? Make sure you click the actual little number 2 to get the little box to appear. That took me a while to figure out, okay? So you do that. Now that you have that, the next thing you could do is right click it and say select data. Right click and select data. Then you have a new way to put your things in here. Select edit, which is right here. Okay, hope you're following. If you're not, you can rewind and watch again. And now you want to put the labels in there. Okay, so, and you have to separate them with commas. So we'll say, what was it? One parent, or let's say both, one, neither. See how I put commas? And say, okay, look at how it changed. And I'm going to close this. Okay, look at how it changed. I'll get a little bit closer so you can see it. That is how you change the actual categories on the bottom. And as you can see, it's a little tricky. Let me just go through it one more time with you, okay? I would start by clicking on the actual axis itself and make sure I get one of those categories when I click. Then I gotta right click it. Then I gotta go to select data. Then I gotta click edit. And then I gotta put my favorite names in there, A, comma, B, comma, C. And then okay. And I was able to change the categories. Okay, so I need you to remember that. That's how you would make a marginal distribution for a set of data. All right. To create a marginal distribution pie chart, here's what you would do. First, highlight the marginal percents that you want to do for a pie graph. So this time, let's do it to these. All right. and oh, the marginal percents you want. I'm sorry, the percents. So let's say we're going to do it for these. All right, so highlight the percents you want, then select the pie chart. So that would be right here, insert, and then get a pie chart, and then hit 2D pie. All right. Oops. All right. So there's my pie chart. Now let's doctor it up a little bit. Change the title by clicking the chart title. College stuff or whatever you're doing. So you could change the title. All right. Next, include percents in the same way that you did before. Click it, get a plus sign. You say data labels and the percents are in there, and that's very helpful. Then you can change the names of the labels in the category by clicking the legend so that a box appears around it and doing select data. So let's get a little bit of a closer look of this pie chart. There is a legend, it's right here. And again, you have to make sure you click the legend the right way. See if it didn't work. Click it one more time, right click, and now we have select data. Once again, say edit, and now say attend does comma does not attend. And look, the labels will be changed. And now you have a nice complete pie chart. Okay. I would say out of all of this is pretty simple. It's just a matter of clicking in the right way. And I tried to make it really, really explicit and clear for you in this guide. I think the most challenging part of this is changing categories because of that edit and the comma thing. But as you can see, it is just a syntax thing. It's a matter of typing it the right way and you'll get the pictures that you want out of it. And that's kind of crucial. Okay. You can use this for all of your classes, for any report you're doing when there's a pie chart. And there are other cases in your homework in Achieve where you'll be asked to think about pie charts and look at them, and you should be able to do that now using these ideas here. Okay, so that's all I have for you when it comes to the Excel guide. Let's go back and talk about Simpson's paradox a little bit now. Okay. All right. So what is Simpson's paradox? Okay, lurking variables are always a problem for interpretation, but their impact can be even more drastic when dealing with categorical data. An association that holds for all of several groups can reverse direction when the data are combined to form a single group. It's pretty deep. Let's talk about it in a very concrete way. I'd like to share with you a really great scatter plot I found online to help illustrate Simpson's paradox right now. And I have it available right here. Here it is. Sorry, I had to find it. I just Googled Simpson's paradox and I found some great pictures. And I want to talk to you about this picture first before we talk about the definitions in our PowerPoint. In this picture, you have the same data, okay? And we did talk about what it would be like to have a staggered or multicolor scatter plot where we use little pink triangles and little orange squares and stuff. That's what you're looking at here. And in this particular data set, we happen to have a bunch of information and data, but if we purposely recode it so that all the people that had a male gender were blue dots and all the people that had a female gender were orange dots, then you could see if we looked at them as two different scatters, look how very different the line of best fit is for each of the two genders versus if I included them all as one large group, it's a significantly, completely different trend line. Okay, so this is what we mean by Simpson's paradox is you don't realize it, but the trend line isn't a negative slope. It's really a positive slope for each of the two little groups you're doing. You just didn't realize you were doing two groups. Simpson's paradox is really something of a it's something of a bug in the computer. It's a monkey wrench in the gears. It's the kind of thing that if you aren't really on top of it, you could totally miss it and totally get the wrong research results. It's crucial to be in tune with all of those little details. For example, this particular study had a very significant difference in the way that, well, it's not a difference, they had a very significant similarity in the way that men do it versus the way that women do it. It's just that in this particular scenario, the men had a little bit of a higher intercept, but they both had the same slope. And if you look, the two trend lines are parallel for men and women. But at least I could say it's a strong slope and it's increasing more than one. Whereas if I just look at all the data all at once together, it's decreasing, and it's not decreasing more than one, it's decreasing slightly compared. So that's Simpson's paradox, is the idea that your data are flawed because you didn't realize that there were more than one category. This goes along very well with our lessons about two-way tables and marginal and conditional probability, because if you say things like the group of data given that they were men, or when they are men, it'll change the way that the data looks. And as you can see, it can be such a change that it can really make your research findings just totally wrong. And that's Simpson's paradox. So in a human way, that's what Simpson's paradox is, my friends. Let me try to explain it to you now with the power slides a little bit, okay? Share that slide one more time. And now as I read it, it might make sense to you. Listen now again. An association that holds for all of several groups can reverse direction when the data are combined to form a single group. So think about the men and women each having a very strong positive trend, whereas the whole group had a slight negative trend, reversed, completely reversed. Okay, the table on the next slide compares the failure rates when removing kidney stones in a sample of patients using one of two procedures. There's one called open surgery, and there's one that's less invasive called PCNL. And here, again, we have a two-way table. And this two-way table, we can see that there are percents on the bottom there. Can you think of a possible lurking variable here? Or is the minimally invasive procedure really riskier than open surgery? Now, that doesn't make sense, does it? Don't you think open surgery should be riskier? Absolutely, most definitely. So why would it be that for open surgery and PCNL, I have a 70% for PCNL and I have a 22% for open surgery, and I have failure and success? The reason why is because if you look at the whole group at the group as a whole, meaning not people that had kidney issues but got open surgery versus people that had PCNL, but look at the whole group altogether, you'll get an answer that is very different. And why is that? Well, it might be because if you look very closely, you'll see that there were just a little bit more people that had a success rate than there were the people that had in PCNL than there were the people that had a success rate in open surgery. Likewise, the failure on the left is bigger, whereas the failure on the right is actually smaller. And it doesn't really make much sense if you look at it, because in one way it's this way and in the other way it's that way. So one option here is maybe you shouldn't be measuring it that way. Maybe you should be looking at the measurements in terms of two different other variables. There's other ways to say it. Maybe we should just do all surgeries or something like that. But in other words, Simpson's paradox does appear here in that way. The procedures are not chosen randomly by the surgeons. In other words, the surgeon can't come in and say, today I feel like doing open surgery. They have to be carefully prescribed, right? In fact, the minimally invasive procedure is most likely used for very small stones with a very good chance of success, whereas open surgery is likely for more problematic conditions, right? And we already kind of knew that looking at it. Note, the majority of the small stones cases, the safer situation, involve PCNL, while the majority of the large stone cases, the riskier situation, involve open surgery. In both cases, the PCNL has a higher percent failure, and the sample sizes causes the overall percent failure to reverse. So this is a little bit, I would say there is another one that we're going to do right after this. I think this is practical, but it doesn't illustrate as well as the next one. So if you're feeling a little bit confused looking at this one, that's okay, because this one's not a very good example. The next one, though, is a very good example, and it'll make it a lot more clear for us. But let's just look one more time at this. You see that the percent failure is different when you do it back and forth with small stones and large stones. In other words, identifying specific conditions. And if you make it a conditional distribution, you have a different outcome than if you just made marginal distributions. Let's talk about this one, though. This will be a little bit more clear for us. In New York State, excluding New York City, that is, of course, this many white men and this many black men died from prostate cancer in 1994. Based on how many white and black men lived there in 1994, the prostate cancer mortality rates are as follows. And I want you to look at certain specific pieces here. First, I want you to come back. I want you to see that we do have a significant, almost equal kind of measurement going on here. These two figures are almost the same number. Look at them, right? They're almost the same number. But these two figures are significantly very, very different numbers. Look at them. Exponentially different, as they would say. And if you consider that they kind of boil down to the same thing, you might say things like, well, there are just as many white men as there are black men who get who died from prostate cancer. Look, 28.7% died of white men, and then there were 28.9% of the black men died. They're the same number, not the same number. And the reason why it's not the same number is because there are significantly less black men than there are white men that had prostate cancer in the study. Look at this figure, 121, versus this figure, 1359. You can't say particularly that they're the same if you have 1,300 white men and 121 black men that have the prostate cancer that died. And as a result of the conditional probability here, if you divide each by their own respective sum, you do get the same percentage for each of them. And it's a little bit misleading because it might make you feel like it's appropriate to say that just as many black men get prostate cancer and die as white men, and that is totally not the case. You could say something like about the same fraction of white men will die as the fraction of black men that will die from prostate cancer. That's practical to say, but that's what we mean by Simpson's paradox. Is your wording is really crucial, and it's important that you know when to use what words and what particular numbers you're using to get your answers, because you might find yourself misleaded and thinking things that aren't accurate. All right, that's what we mean by Simpson's paradox. A little bit more analysis of this case. Cancer mortality rates are similar in both groups. Like we said, they're both about 28%. But when the data are broken down by age group, we see that black men had a much higher rate. Now look at the new conditional distributions and look at what they say. Here we have, if we break it down by age, which we had not discussed before, but if we break it down by age, we see a significant massive change. Look at these figures here. And then look at these figures right here. What is the source of this example of Simpson's paradox? Why is this happening? Why does it look here like as if we have so many more people on the bottom than we do on the top? And the reason why is because we have a much larger sample in one than we do of the other. All right. Now, when it comes to Simpson's paradox, it's conceptual. It's an idea. You'll be asked questions about it in Achieve, and they'll discuss different specific pieces of it and try to help you learn the idea of how you have to. It's the point of it is, my friends, that you really have to look at it like a scientist when you're researching, doing stats. You have to really very, very carefully dissect every little piece of it to make sure that you're on track with what you're trying to say. It's so easy to make a very honest mistake and look at a two-way table and come up with a conclusion that's inappropriate. Like, for example, that the same amount of white and black men have prostate cancer have died, and it's not true. Maybe the same percentage of the population of them or something like that, but be careful with your wording. All right. So I hope that was helpful, and I really appreciate your patience with this course, the way that it has gone. So far, it looks like everybody's on track with the achievement. I want to commend you for that. Thank you for your very close attention to your homework. That's why I'm going to be doling out all kinds of A's, and I can't wait to see everybody get an A or nice high grades. Remember, if you're having issues, that you can reach out to me and I can extend things for you. Tutoring is available on campus to help as well. And for the most part, that's all I have for you today. I hope that was helpful for you. Now what I'd like to do is end our class. I'm going to pause our recording. And for those of you who are here paying attention in the live Zoom, I'll open the floor to questions at that point. But in closing, I just want to say thank you so much for your close attention to my lesson, and I hope you all have a wonderful weekend.